Good evening. In this video, we are going to talk about proposition 26 from book 1. Okay, so this proposition declares given two triangles and two angles equal to each other respectively, and a side is equal to another side. It can be an adjoining side or an opposite side to an angle, and then these two triangles are equal, which means the related sides are equal and the remaining angles are equal. So let's give it a proof. So it can be divided into two scenarios. Let's prove them one by one. So in the first case, let's suppose that angle A equals to angle D, they are equal, and angle B equals to angle E, so they are equal. And in this scenario, let's suppose the equal side is the adjoining side between two angles. Okay, so which means AB is equal to DE. And we would like to use the method of contradiction again. So let's give it a suppose that we make a hypothesis here that AC is not equal to DF. Okay, and for convenience, let's just assume AC is less than DF. Okay, so please recall proposition 3 that we are able to cut off, let me see, DG, which is equal to AC, right? Because DF is longer than AC. And then using postulate 1, we are able to join GE together to construct this straight line. Okay, so we know that AC is equal to DG, right? And angle A equals to angle D, right? And AB equals to DE, right? And then apply proposition 4, side angle side. We see that side angle side, so these two triangles are equal. ACB equals to DGE, which means the angle B is equal to angle GED, right? So they are equal. But we have already known that angle B is equal to angle E. So apply combination 1, things equal to the same are equal. We know that if we combine these two equalities together, let's say angle B equals to angle which is FED, combine them together, we can imply that angle GED is equal to angle FED, right? So GED equals to FED. It absolutely breaks this combination 5, where it says the whole is always greater than the part. So we see that DEF, angle DF is a whole, but it is equal to the part DEG. This is impossible, so it breaks the combination 5, and our hypothesis is incorrect, which means AC must be equal to DF, right? So if AC is equal to DF, let us add this condition here. So AC equals to DF, and we know that angle A is equal to angle D, as well as AB equals to DE, right? Combine them together and apply proposition 4 again, side angle side, right? We know that triangle CAB equals to triangle FDE, which means related angles and related sides must be equal to each other. So this proves our first scenario. And let's move to the second scenario, where the side is the opposite side to an equal angle. Okay, so let's assume in this scenario, in this scenario we are given condition like angle A is equal to angle D, angle B equals to angle E, exactly the same as previous, but at this time the opposite side will be equal, which is AC, let's suppose, equal to DF. Okay, so we are given these three conditions. And let's use method of contradiction again. So we hypothesize that AB is not equal to DE. And also for convenience, let's suppose AB is less than DE. Okay, AB less than DE. Write them down. So similarly, we can apply proposition 3 and get cut off DG here, where DG is equal to AB. Okay, so we have DG is equal to AB, and using postulate 1 we are able to join FG, right? And please pay attention to this triangle. What we know DG equals to AB and angle A equals to angle D. This is a condition, right? And we also know that AC is equal to DF. This is another condition, right? So we combine them together and apply proposition 4 again, side angle side. We know side angle side. We know that these two triangles are equal, which means so it implies that angle B is equal to angle FGD, right? They are equal. And please pay attention to this triangle FGE. This angle FGD is an exterior angle of this triangle, and angle E is an opposite interior angle, right? And what we have proved in proposition 16, please recall it. The exterior angle of a triangle will be greater than any of the two opposite interior triangles, right? So angle FGD, so we have angle FGD must be greater than this opposite interior triangle, angle E, because of proposition 16, right? And if we combine this equation, equality, and this equality together, angle B equals to angle E, then we know that using combination 1, we know that angle E is equal to angle FGD, right? And this equality and this inequality, they are absolutely contradictory to each other, which means our hypothesis is false. So AB must be equal to DE, right? And if we apply AB equals to DE and angle A equals to angle D and AC equals to DF here, the given condition, we apply proposition 4 again, side angle side. We know side angle side. We can imply that, let me write it left side. Angle ABC is equal to angle, triangle DEF. which means remaining related angles and related sides must be equal to each other respectively. And this proves our scenario 2. And if we combine them together, we proved our proposition. This is the end of the proof, okay? And I would like to add a bit of the information about congruence triangles. As we talked about congruence triangles before, if you can still remember, proposition 4 states that if we have side angle side relationship, these two triangles are congruent. And proposition 8 proves that we have side equal relationship, then the triangles are equal. And in this proposition 26, we have add another congruence theorem, like 26, it will be, let's call it angle S, or probably angle side angle, okay? So this is another congruence theorem of it, but as Euclid has never declared or defined what is congruence, he had never defined this concept. So in the book of elements, let us just respect to the original one and use equal. So we say triangle 1 is equal to triangle 2 rather than congruent, which is probably nowadays more precise, okay? And if you are interested in this kind of topics, just refer to congruence triangle or congruent triangle, okay? This is the end of the video, and in the next video we are going to talk about proposition 27. So thanks for watching, have a good day.